Good evening, everyone. Welcome to NPTEL tutorial session for the course Principles in Organic Synthesis. So, this is our week 11 tutorial session, that is our 11th tutorial session. So, today we will be discussing mainly the contents of the week 11 lectures, and then we will be discussing some of the problems related to those topics. So, let me share my slides first. I hope my audio, I am audible to you. If you are facing any problem in between for following, or if you are having any doubts in between, feel free to ask. Okay, so in the week 11, mainly we have seen five lectures. There were total of five lectures. And in the first lecture, we have seen the applications of the diazonium salt. And in the second lecture, we have seen some rearrangement reactions. In the third lecture, also, we have seen some rearrangement reactions of halogens, oxygen, sulfur, and nitrogen containing centers. Then in the lecture 4, we have seen the rearrangement to electron rich carbon, and in the lecture 5, we have seen the reagents containing phosphorus and some reactions related to those topics. So, mainly in the lecture 3, we have seen the application, lecture 1, we have seen the applications of diazonium salts, that is synthetic importance of diazo coupling, where this diazo compounds can be used as neutral dyes, acidic dyes, or basic dyes. Modern dyes like Parared, Orange 2, Bismarck Brown R, or Alizarin Yellow R, or the iso compounds are also used as indicators like methyl red, methyl orange. Then we have seen diazonium salts compounds are utilized in the synthesis of amines, quinones, and then they are utilized in the palladium catalyzed cross coupling Heck Matsuda reaction for the synthesis of stilbene. Then in Sonogashira coupling as well, where we can use them instead of aryl halides, aryl diazonium compounds can be used. So after that, we have seen several reactions. Like in the week 11 lectures, we have seen a plenty of named reactions. So maybe we can quickly go through some of those reactions and some of those rearrangements very quickly before starting the problem solving session. So first we will see some rearrangement reactions. So the first one is Wagner-Mervin rearrangement. Okay, so Wagner-Mervin rearrangement is basically an acid catalyzed reaction which involves the alkyl group migration of alcohols to give more substituted olefin. So the product we are getting here is more substituted olefin, and here our reactant is an alcohol and the reaction medium is acidic medium. So here what is happening is that first, yeah, first in the presence of this proton source, this hydroxyl group in our reactant starting material will get protonated, and then followed by the elimination of water molecule will result in a carbocation. So as we can see here, this is a secondary carbocation. So what is favoring this 1,2 alkyl shift is the formation of a more stable tertiary carbocation. As we all know, the order of stability of carbocation is primary greater than secondary carbocation greater than tertiary carbocation. So if there is a possibility for the tertiary carbocation by the migration of some group, the starting material will or the intermediate will always prefer the migration to form a stable carbocation. So here what is happening is that 1 to alkyl shift is happening, so that this R group will migrate over this position. So the carbocation will be shifted from this center to this center, so we will get the stabilized tertiary carbocation. Then this loss of proton will be giving this substituted olefins, more substituted olefins. So this is known as Wagner-Mervin rearrangement. So it is basically the acid catalyzed alkyl group migration of alcohols to give more substituted olefins. So here as we can see, this OH group and this proton is not there, as well as this R group migrated to this center, and here a double bond has been formed. So these are the changes that is occurring in this Wagner-Mervin rearrangement. So I hope this is clear. Maybe I'll give 2 minutes to just quickly go through this, then we can go to the next reaction. So that is about Wagner-Mervin rearrangement. It is basically a reaction which changes the carbon skeleton of this reactant by moving one hydrogen or alkyl or aryl group depending on the migratory aptitude as well, to from one carbon to the adjacent carbon. That is why we called it here 1,2 alkyl shift. The migration is happening from one carbon to the next carbon adjacent to it. So it is basically nucleophilic rearrangement that involves this 1,2 migration of ring carbon atom. And maybe this can also be called as a sigmatropic type of rearrangement which proceeds with stereochemical retention. And the main driving force behind this reaction is the rearrangement is happening because a tertiary carbocation is more stable than a secondary carbocation, which is followed by primary carbocation. And as we can see, it is useful technique for generating complicated structures with the carbon-carbon bonds in positions which are difficult to access by normal chemical synthesis method. Moving to our next reaction, that is pinnacle rearrangement. So pinnacle rearrangement, here we can see we are using vicinal diol. So vicinal diol is the presence of hydroxyl group on adjacent carbon atoms. So this 1,2 position, this 1,2 substituted diols will be called as vicinal diols. And in presence of this heating condition and acidic condition, it is rearranging into form this ketone. So as we can see here, there is only 2 methyl groups on this carbon, but here there are 3 methyl groups on this carbon, and here one of the methyl group out of this two has been migrated to the next carbon, and this hydroxyl group have been converted into ketone, and one of the hydroxyl group have been removed. So the first step is same as that of the Wagner-Mervin rearrangement. So in the first step, this OH2 plus, that is one of the hydroxyl group, will get protonated, and it will eliminate the water molecule to form this carbocation. Then again, what is happening, this oxygen lone pairs will fall over here, and this one of this methyl group is like attacking over this carbocation carbon center, so it will form here and resulting in the formation of this oxonium ion. Then what is happening again, this loss of this proton from this oxonium ion will result in the formation of this ketone. So the acid we are using here to protonate this hydroxyl group, giving the good leaving group water molecule, and that will leave, which result in the formation of this carbocation. And then what is happening, this carbon oxygen pi bond is forming, that is this pi bond is getting formed along with the migration of the carbon atom. So this is getting migrated and this bond is getting formed. So that is a key step of this reaction, formation of carbon oxygen pi bond with the migration of the carbon atom. So here we have seen the case with this vicinal diol, which is symmetrical. That is, on both the carbons, all the substituents are same. If we had unsymmetrical diol, then like The major determining factor will be is that which is more prone to form a carbocation, like out of the two carbon oxygen bond, which will form a carbocation more readily, either this or this. That will be the determining whether in the case of unsymmetrical diode. But here anyway, if it is protonating here or here, both the cases it will be the same only. So in this case we will get the single product only. But in the case of unsymmetrical diode, there is possibility of different hydroxyl group getting protonated and different carbocations resulting. So that will give result different product as well, and the major product is determined by which of the two carbon OH carbons will form a carbocation more readily. So that is pinacol rearrangement. That is pinacol means vicinal diol is getting converted into ketone. 1,2 diols basically is getting converted into this carbonyl compounds such as ketones or aldehyde through an acid catalyzed and dehydration process, because water molecule is also getting eliminated in this process. That is basically pinacol rearrangement. And here also, as we seen in earlier case, that 1,2 shift of the substituent is taking place. Okay, so those were two rearrangement reactions. Now we will be seeing some rearrangement reaction of halogen, oxygen, sulfur, and nitrogen containing centers. That is, this were basically involved in this lecture 2, and now we will be seeing some reactions from the lecture 3, that is the rearrangement of halogens, oxygen, sulfur, and nitrogen containing centers. So this one such reaction is this Ruppe rearrangement. So this is also an acid catalyzed rearrangement. Sorry for the poor quality of this slide. So this is an acid catalyzed rearrangement where this tertiary alpha acetylenic alcohol. So this is tertiary alpha acetylenic alcohol. So as we can see, here is one acetylenic group, and to that carbon we have another carbon which is having a hydroxyl group. And yeah, so the product we are getting is this alpha beta unsaturated ketones, and we are not getting this alpha beta unsaturated aldehyde. So this reaction is known as Ruppe rearrangement. So the difference between this Mayer-Schutzer rearrangement and this Ruppe rearrangement is that in the case of Mayer-Schutzer rearrangement, we can get this alpha beta unsaturated aldehydes, but here we will be always getting alpha beta unsaturated ketones. So let us see the mechanism of this reaction. So first we know in the presence of this acid, this alcohol is getting protonated and it will eliminate to give a positive charge over this center. That is, this is a carbocation, and to stabilize that carbocation, one proton is leaving. So here the double bond will be formed and this carbocation will be stabilized. Again, what is happening, this alkyne is getting protonated. So if this center is getting protonated, we know this center will be getting a positive charge. So this is a carbocation over this center. Then to that again the water molecule is attacking, OH minus is attacking. So we will get this kind of intermediate, and then this that is, this is basically enolic form, and once it tautomerizes we will get the corresponding ketone. So that is this acetylenic alcohol is giving this alpha beta unsaturated ketone. I have kept a more clear view of the reaction. So this is the reactant. We have this alkyne, and here we have this hydroxyl group. We are getting this alpha beta unsaturated ketone also. So first step is the protonation, then water molecule is leaving, resulting in this carbocation. This deprotonation will result in this compound. Then again terminal alkyne is getting protonated to form this carbocation, upon which a water molecule is attacking. Deprotonation will give this enol form, and that can be tautomerized to this alpha beta unsaturated keto form. Okay, this is another pathway which it can follow. That is, first this alkyne is getting protonated to form this carbocation over this center, and then this oxygen lone pairs is attacking over this carbocation to form this epoxide kind of compound with this positive charge on. Yeah, this epoxide compound with a positive charge on oxygen. Then this proton will leave and this bond will open up to get this enol, which upon tautomerization we will get this ketone. So the difference between these two mechanisms, as we can see, is that here the hydroxyl group is coming, that is, this oxygen is coming from the reaction medium. That is, intermolecularly the reaction is happening, because first of all the water molecule is leaving, and then another molecule of H2O from the reaction medium is attacking over this carbocation center to get this ketone. But here, as we can see, whatever oxygen is already present in the reaction starting material, that is preserved in this product. So this reaction is going through an intramolecular pathway, we can say. So this reaction is known as Rope reaction. So this is the rearrangement reaction involving oxygen center. Next, we are going to see the some rearrangement reactions involving nitrogen center. So we will be seeing Curtius rearrangement, Schmidt rearrangement, Hoffman rearrangement, Lawson rearrangement. Almost everything is proceeding through the same intermediate or similar intermediate, we can say. Okay, let's see. So first one is the Curtius rearrangement. So here what is happening, our reactant is this acid chloride, which we are treating with an acid, which can be NaN3 or anything which is we are basically using. So this N minus of this acid is attacking over this carbonyl carbon center, and this bond is shifting to here. Once it come back, Cl minus will be eliminating to give this acyl acid. And then what is happening, this negative charge on the nitrogen will fall over here, and this bond will shift over here to form this intermediate, and this N2 elimination upon heating will take place to form this nitrene intermediate. And once this nitrene is formed, what can happen is that this alkyl group attached to this carbonyl carbon center can migrate to this nitrogen sender. So this lone pair of this nitrogen will shift over here to form this isocyanate. So this isocyanate is the key intermediate in the case of Curtius rearrangement. And if we are treating this isocyanate with this alcohol, R dash will be attacking over this oxygen, and this um, OR dash will be attacking over this oxygen, and this H will be attacking over this nitrogen. If we are treating with water, OH minus will be attacking over this not oxygen, carbon, and this H plus will be attacking this nitrogen will take this H plus. If we are treating with secondary amine, this H plus will be taken by this nitrogen, and this R2N, this nitrogen lone pair, can attack at this carbonyl carbon center. So by the elimination of this carbon dioxide from any of this product, the finally we will be getting this amine. So basically the reaction is the conversion of this acid chloride into this amines through an isocyanate intermediate. So I hope this is clear. So first this acid will attack over this carbonyl carbon center. Cl minus will be leaving to get this acyl acid. Then N2 elimination will give the nitrene. Once nitrene is formed, this alkyl migration is happening to get this isocyanate. Isocyanate is R N double bond C double bond O. Then it can either react with amines or hydroxyl, the water molecule, or alcohol to give amides basically, and then elimination of this carbon dioxide we will be getting this amine. So the conversion of acid chloride to amine in the presence of this acids through an isocyanate intermediate, which again is through a nitrene intermediate, is known as Curtius rearrangement. Okay. Moving to the next reaction, which is also an rearrangement reaction, which is also a rearrangement reaction, which is proceeding through this isocyanate. So here, what we are taking is we are taking this compound, that is we have this amide, and that is nitrogen is substituted with this alcohol. So it is basically hydroxyl substituted amide, which upon reacting with this acyl chloride or this sulfonyl chloride, we will be getting this X substituted with this acyl group, or this what to say, acyl group, or this sulfonyl group, we will be getting this intermediate. Then when this hydroxyl group will take up this proton, that will form this negative charge over the center, which will come here, and this bond will shift over here to form this intermediate. Again, this O minus, when it comes to here, this R group will migrate it to this nitrogen, and this OX is leaving to form this isocyanate. Then in the presence of this water molecule, again as we saw earlier, we will be getting this carboxylic acid, not carboxylic acid, this what to say, so what is happening is that this H2O will be attacking over this carbonyl carbon center to form this intermediate. And once it is formed, this nitrogen will take up a proton, this bond will come over here, and this will take up a proton to form this compound, which upon the CO2 elimination, we will be getting this amine. So this is also proceeding for through this isocyanate, and the product is also the same. Here we had this acid chloride, here instead of that, this hydroxylamine kind of thing is there near to ketone, and the product we are getting here is also same, that is amine. And the reaction is proceeding through the same isocyanate intermediate. But here, as we can see, this nitrine is not directly involved. Here this O minus is coming here, and same time R group is migrating over this nitrogen center, and this group is leaving to form this isocyanate intermediate. Moving to the next rearrangement reaction, that is Schmidt reaction. So here also, what is happening is that we are taking a carboxylic acid. Carboxylic acid initially will get protonated, then followed by the elimination of water molecule, we will be getting this intermediate, which can exist in this form as well. Then we are again treating with this azide, and this nitrogen N minus will be attacking over this carbon, this bond will come over here to form this intermediate. And when this N2 is leaving, we will be getting this isocyanate kind of compound. And then upon protonation, upon this water molecule attack, again we will be getting the same intermediate. So here also, after the isocyanate, we are getting the same product as well through the same pathway. So till the isocyanate only, the reaction is different, because first case we are using an acid chloride, and instead of that, here we are using this carboxylic acid. So acid chloride, directly the Cl minus is leaving, so here we have to treat with an H plus to make this a good leaving group by protonating that hydroxyl group. So remaining, the reaction is proceeding through the same, not same exactly, similar pathway. And this reaction is known as Schmidt reaction. Moving to the next reaction, that is Hofmann rearrangement, which is also proceeding through the same isocyanate intermediate. So here we are converting an amide into this amine. So here what is happening is that first, in the presence of a base, that will take from one of this amide proton to form this intermediate. Then when we are treating with this bromine, that will, this N minus will attack this Br plus and Br minus will leave to form this intermediate. And then again treating with base, this will form this N minus, and that N minus can fall over here and this bond will shift over here. And once it is coming back, what is happening is that this O minus will come back, this R group will migrate over this nitrogen, and Br minus will be leaving to get this isocyanate. Then again water molecule is attacking over the center, this bond will shift over here to get this compound, and then this proton is leaving, and then this will come back, this will take up a proton to get this compound, which upon this decarboxylation we will be getting this amine. So Hofmann rearrangement is amide to amine. Curtius was acid chloride to amine, Schmidt was this acid to amine, Hofmann is this amide to amine, and the Lawson rearrangement was hydroxylamine kind of compound to amine. So everything is proceeding through the same isocyanate intermediate. So these are the four examples for the reactions involving nitrogen center: Curtius, Lawson, Schmidt, and Hofmann rearrangement. Moving to the next reaction, that is Baeyer-Villiger oxidation, which is a rearrangement reaction happening through the oxygen center. So this ketone, when we are treating with this MCPB and DCM, what is happening is that this oxygen is getting inserted and we are getting this ester. And this is the reactivity order: tertiary, then secondary, then aryl or vinyl, and then primary. So the mechanism is that MCPBA, which is this one, metachloroperbenzoic acid. So this R group is aromatic ring, and which upon this reaction with this ketone, this oxygen will get protonated by taking this proton, and this will form O minus and this will be OH plus. Then this O minus will be attacking over this carbonyl carbon center, this bond will shift over here to get this intermediate. Then oxygen lone pair will fall over here, and this peroxide linkage, this will leave as this group, and we will be getting this compound, which upon deprotonation we will be getting this ester. So the mechanism I have written here as well. So first, this peroxy acid protonates the oxygen of this ketone to form this compound, and then this peroxy acid O minus attacks the more electrophilic carbonyl carbon, which will result in the formation of this intermediate, which is known as Krieg intermediate, CRIEG. G E E, Krieg intermediate, and then one of the substituents of the ketone. So this R group is basically migrating to the oxygen of the peroxide. This R group is migrating over here, and this bond is getting cleaved, and this is leaving as ROR minus. Okay, so this R group is migrating over this oxygen center, and this is leaving us this group, and we will be, so this will be basically what this R is our benzoic acid from this MCPBA. So that will be leaving us benzoic acid, and we will get this, which upon deprotonation we will get this ester. So here also this 1,2 migration is happening, but not between carbon carbon center. Here the migration is happening between carbon and oxygen center. And so this is the order of that migration, then tertiary, secondary, then aryl or vinyl, then primary. So that is the mechanism of this Baeyer-Villiger oxidation. First protonation of ketone by the peroxy acid, then this will attack over this carbonyl carbon center to form this Krieg intermediate. Then this R group migrate to this oxygen to form this intermediate, which upon deprotonation we will be getting this ester. Okay, now we will see the rearrange. So these we will be seeing. Yeah, this is also a kind of Baeyer-Villiger oxidation. So the first step is almost similar. This oxygen is getting inserted by using this MCPBA or H2O2 NaOH condition. We will be getting the substituted orthoacyl phenol, which upon hydrolysis we will get the proton here, and OH will go this side. So this will leave out, and we will be getting the substituted phenol. So this reaction is known as Dakin oxidation. So the mechanism is almost similar. First, the O minus from this peroxy acid peroxide will attack over the center to form this tetrahedral intermediate. Then this 1 to aryl shift is happening because this benzene ring is having more migratory aptitude, that will migrate to this oxygen center. This OH minus will be leaving to form this O acyl phenol. Once this O-acyl phenol is formed, then what is happening? OH minus will attack over this carbonyl carbon center, and that will form this intermediate. Then again this will get protonated. This will leave us water molecule to form this intermediate, and then OH minus will take this proton to form this intermediate, and then what is happening? This negative charge is shifting over here, and this is leaving to form the give leave out this acid, and we will be getting this substituted phenol. So this is known as Dakin oxidation. So this is also a rearrangement reaction involving 1,2 migration utilizing the oxygen center. Moving to the next reaction, which is a rearrangement to electron-rich carbon atom, that is Somlet-Hauser rearrangement. So in Somlet-Hauser rearrangement, what is happening is that this Tertiary benzylic amine is getting alkylated. That is, nitrogen will attack over this center, nitrogen lone pair is attacking over this, and X minus is leaving to form this benzylic quaternary ammonium salt. Then in the presence of the base, this proton is getting abstracted to form a negative charge of this, that is a nitrogen halide, because there is already a positive charge on the nitrogen atom, and now a carbon atom is having the negative charge. Then what is happening? This, yeah, this 2 3 migration is happening, that is, yeah, we will see the mechanism. So first, as we saw, this nitrogen halide is forming, which is generated from this benzylic quaternary ammonium salt by removing the acidic proton using a strong base. Then this sigmatropic rearrangement is happening, as we can see here, a 2 3 sigmatropic rearrangement. So the CH2 minus is here, so that will be attacking over this center. Then whatever this bond is there, that will go over here, and this is shifting over here this side to stabilize this positive charge on nitrogen. It will form this intermediate. Then upon regaining the aromaticity by losing this proton, we will get this compound, substituted tertiary benzylic amine. So initially we are taking a tertiary benzylic amine. Here we are getting a substituted tertiary benzylic amine through this Somlet-Hauser rearrangement. So once this negative charge is formed here, yeah, this negative charge is formed over this center, that will attack over this carbon, and this bond will come to here, and this bond is breaking to form this intermediate via this 2 3 sigmatropic rearrangement. Then this rearomatization, we will be getting the product. So this is the Somlet-Hauser rearrangement. So far we have seen the rearrangement reactions happening to the electron deficient carbon. So here we can see it is happening through this electron rich carbon atom. The next one is Favorsky rearrangement. Here also this rearrangement is happening through this electron-rich carbon atom. So this alpha bromo compound, upon treatment with this nucleophile and a base, we are getting this rearranged product. So here is a mechanism. Firstly, the base will be taking the proton. So here in this case, it will be taking this proton to form this enolate. And once this enolate is formed, this O minus will come over here, and this double bond will attack over this center, and this X minus will be leaving to form the cyclopropanone kind of intermediate. And to that carbon, nucleophile is attacking, then O minus is forming. Then again what is happening? This O minus, when it will come back, this bond will take up the proton, and we will be getting this compound. So basically what is happening here is that this ring contraction is taking place. That is, we used initially this 6 membered ring, and here we are getting the 5 membered ring. So Favorsky rearrangement is basically used for ring contraction reaction. So first, this deprotonation of this alpha proton to form this enolate ion, and then this enolate will cyclize by the elimination of this leaving group to form the cyclopropanone intermediate. Then the nucleophilic attack over this carbonyl carbon center, and when the O minus will come back, this bond will be opening up to form the ring contracted product. This reaction is known as Favorsky rearrangement. So next we will be moving to some reactions involving phosphorus. So the many reagents contains phosphorus in their constituent like sarin, malathion, which are a toxic nerve agent and insecticide. And the uniqueness of phosphorus is that, or the uniqueness of phosphorus containing reagents is the availability of d orbitals for bonding, formation of the strong bond with oxygen and sulfur, and then it can exist in p3, can be oxidized to p5 oxidation state. So one of the reaction involving this phosphorus is Wittig reaction, which is a homologation reaction where this ketone is converted into this alkene by using this phosphorus halide. So first what is happening is that this pph3 will attack over this carbon, and that will be forming this intermediate preparation of this phosphonium salt. Then base will be taking this proton to form this negative charge, and that negative charge will attack upon this carbonyl carbon center, and this bond will shift over here. So we will be getting this intermediate. Then this O minus can attack with this phosphorus to form this kind of a tetracyclic intermediate. Then what is happening is that this triphenyl phosphinoxide is a like very good leaving group. It will leave out, and we will be getting this alkene as the major product. So this intermediate is known as oxaphosphatane intermediate, for membered intermediate having oxygen and phosphorus. So first step is the preparation of the phosphonium salt, that is by treating this alkyl halides or aryl halide with this pph3, we will be getting this phosphonium salt, which upon treatment with the base we will be getting this ylide, and then nucleophilic addition of this ylide to this carbonyl carbon, which will result in the formation of this oxaphosphatane. Elimination of the triphenyl phosphinoxide gives the isadalkene. So mostly isadalkene will be favored because considering the steric reasons. So this reaction is one of the example for the reaction involving phosphorus reagent, and this reaction is known as Wittig reaction. Then the next reaction is Mitsunobu reaction. So this we have already discussed previously also, which is basically an SN2 type of reaction where we are getting this inverted product. So firstly, the pph3 will be attacking over this diethyl azo dicarboxylate to form this intermediate. Then this nucleophile is generated by taking the proton by this nitrogen, and then this oxygen will coordinate with this phosphorus, and this will be leaving out this hydrazine kind of intermediate to form this intermediate. Then nucleophile file will be attacking in an SN2 fashion to leave this triphenyl phosphinoxide, and we will be getting this inverted product. So that was the sum of the reactions where we have seen, which we have seen in the week 11 lectures: Wagner Merwin rearrangement, Pinnacle rearrangement, Ruppe rearrangement, Curtius rearrangement, Lawson rearrangement, Schmidt reaction, Hoffman rearrangement, Baer-Villiger oxidation, Dakin oxidation, Somlet-Hauser rearrangement, Favorsky rearrangement, Wittig reaction, Mitsunobu reaction, and some more reactions we will be seeing during the problem solving session. Now we will move on to the problems. The first question is the major product of the reaction, that is this compound upon treatment with the silane and heating condition, which will be the major product. So this is the correct answer. So as we can see, a migration is happening of this group from this oxygen center to this carbon center. So the reaction is Claisen rearrangement, which we know is basically a 3,3 sigmatropic rearrangement. So here the basic mechanism of sigmatropic rearrangement is that this aryl allyl ethers, so aryl and allyl group is there, aryl allyl ethers undergo 3,3 sigmatropic rearrangement by heating to form this allyl phenols. So here what is happening is that if we number this, we will be getting here as this is 1, this is 1, 2, 3, 2, 3. So this 3 3 bond will be forming and this 1 1 bond will be breaking. So this 3 3 bond will be forming like this, and this 1 1 bond is breaking. So basically what is happening here is that this is attacking over this center, this whatever aromatic bond is there, that is shifting over here, and this is breaking and that is coming over here. So we will be getting this compound upon rearomatization. So the detailed mechanism is here. This will attack over this will shift over here, and this bond is breaking to form this intermediate, which upon rearomatization we will be getting this product. This is another example for the same thing. That is, this group is attacking over the center, then this is coming over here, and this bond is coming over here. 3 3 sigma tropic rearrangement to form this quinone kind of intermediate, then deprotonation will be resulting in this regaining of aromaticity to get this compound. So 3 3 sigma tropic rearrangement. So oxygen we are naming as numbering as 1, and the allylic carbon we are numbering as 1, then 1 2 3, and here 2 3 3 3 bond will be forming and 1 1 bond will be breaking. So this reaction is known as Claisen rearrangement. So as it is written here, if the ortho position is blocked, then only the rearrangement continues to give the para product. Here also in our case ortho position is free. So first preference will be always given to ortho position, and if it is not free, then only the group will attack over the para position. So this is the next question. This amide we are treating with this PIDA, that is diacetoxy iodobenzene, and then KOH in presence of this isopropanol, which will be the major product. So in the problem solving session, we will be seeing the uh, like named reactions which we didn't discuss in the beginning, so that almost all the reactions we will be covering in today's tutorial sessions, whatever professor has taught in the week 11 lectures. So here the correct answer is this amine, and the reaction is Hoffman rearrangement. So this already we have seen. So what will be happening first is that, so I'm not going into this mechanism, I will explain here. First, this iodine will attack over this center, and this will be H. And then what is happening here is that then again the deprotonation will be happening. That time it will be like N, and here N minus will be there after deprotonation. Then this group migrate over this center, and this I minus will be leaving out to form that isocyanate intermediate, that is double bond O, double bond C, double bond N, and the R group will be there. Then upon hydrolysis and decarboxylation, we will be getting this amine as the major product. So this is an example for Hoffman rearrangement. We have already discussed the detailed mechanism for all the reaction, four reactions involving the nitrogen center, that is Curtius rearrangement, which was the starting material was acid chloride. Then this Hoffman rearrangement with the amide, Schmidt reaction with carboxylic acid, Lawson rearrangement with the hydroxylamine. So everywhere we are getting the rearranged product as the amine. Moving to the next question, the major product of the reaction. So here this compound we are treating with this NaOH and then acidic condition, which will be the major product. Okay, so here the correct answer is this one, that is option B. So this is an example for benzylic acid rearrangement, which is a rearrangement of 1,2 diketones that have no alpha hydrogen. So here also we have 1,2 diketone without having any alpha hydrogen, which upon reacting with this hydroxide ion, we will be getting this alpha hydroxy carboxylic acid. So here we are getting this alpha hydroxy carboxylic acid, and this driving force of this reaction is the formation of a stable carboxylate salt. So what is happening initially is that this OH minus is attacking over one of this carbonyl carbon center. Let it be this one if we are seeing first. So this will be like this. It will be O minus will be here and OH minus will be here. Then when this O minus will come out, this group is migrating over this center. So first I will explain this, that will be better. So H minus will attack upon this carbon and that will give this intermediate. When this O minus will come back to here, this pH will attack over this center and this will be coming to here to form this intermediate. Then in presence of H2O, it will form this benzylic acid. So that is also what is happening here as well. So here also, as we can see, OH minus is attacking over this center. For example, O minus is coming over here, and once it is coming back, this bond is attacking over this center. That is, this bond is migrating to this carbon, and this is O minus, which will in presence of H plus that will be converted into OH. So this is the example for benzylic acid rearrangement. So it is initiated by the attack of this hydroxyl ion to this center. So which is the stable carboxylate salt? If it is attacking over here and forming the stable carboxylate salt, that will be the more preferred pathway than this one. Moving to the fourth question. So the major product of the reaction. So we are treating this carboxylic acid with this oxalyl chloride, then this diazomethane, and in this third step with this silver carbonate, sodium carbonate, and this sodium thiosulfate, which will be the major product out of the four options given here. Okay, so here the correct answer is this carboxylic acid. So as you can see, the difference between the starting material and the product is this is homologated product. So what is happening here is that this aren't acid homologation reaction. So first, this carboxylic acid is getting converted into this acid chloride by using this thionyl chloride or oxalyl chloride. So we will be getting this acid chloride, and then this once this acid chloride is formed, this methane, which is basically the CH2N triple bond N plus and CH2 minus, that will attack over this acid. So we have now this C double bond O Cl, we have this. So this negative charge will attack over this carbonyl carbon center. This bond will shift over here, and when it is coming back, the Cl minus will be leaving out to get this kind of intermediate. Then yeah, Cl minus will leave out to get this in what. So what we will be getting? We will be getting this C, this CH2 N2, and here it will be double bond O, right? Yeah, so we will be getting this, and then what is happening is that when we are treating with the silver oxide Na2CO3 Na3S2O3, what is happening here is that this negative charge, this enolite formation is happening. This will fall over here, and this will come back to here to get this kind of intermediate. And when this is coming out, what is happening is that this N2 is leaving, and this whole group is getting migrated to this carbon. I will once again draw. So now we have this C double bond O CH2 N2. So in treating with the silver oxide sodium bicarbonate, proton will be abstracted from here. So that will create a negative charge which will go to here, and this bond will shift to here. And when this bond is coming back, what will happen is that this whole group will migrate over this carbon, and this N2 will be eliminated. I think it's more clearly represented here. This bond will come back, this group will migrate over here, and this N2 will be leaving to form this ketene. So this anti-acid homologation reaction is happening through this ketene. Ketene is basically C double bond C double bond O. This kind of intermediate compound is known as ketene. So then it will get hydrolyzed, that is OH minus will be attacking over this carbon center, and H plus will be taken by this proton to form the corresponding carboxylic acid. So this reaction is known as anti-acid homologation reaction. I hope the mechanism is clear. So here this carbon number is getting increased, and we are getting the same uh, carboxylic acid as the product but homologated. So first step is the conversion of carboxylic acid into acid chloride, then converting it into diazo compound, then treating with silver oxide, the enolite formation, and then migration is happening to get the homologated product. Moving to the next question. The major product of the reaction, this compound upon treatment with the sodium aside, this methane sulfonic acid in DCM. So I think this also we have already discussed, so I am not going into the details. So this is an example for Schmidt rearrangement. So what is happening here is that first, in the presence of this Na N3 minus will attack over this carbonyl carbon center, and that will N2 will leave, and that will result in the formation of an isocyanate. And once that isocyanate is formed, that can undergo rearrangement, and we will be getting this. That is, once that isocyanate is formed, it will be like N double bond C double bond O here, Me also will be there, and then here that other group is there, R group. So then what is happening is that this methyl group is basically migrating over this center, and this bond is shifting over here. No, that methyl group is not migrating here. Yeah, once that, here it will be like double bond. I have drawn the wrong intermediate, so here we have this C double bond O and 3 minus will be attacking over this carbonyl center, so it will be double bond O, then N, double bond N, double bond N, plus minus. So the once N2 is leaving, we will get this N, double bond C, double bond O, and this carbon is already having this methyl group, and this carbon is having this other R group. So then this R group is migrating over this center, and then this bond is shifting over. This is like it is getting protonated, we can say, or this is shifting over this, because carbocation will be generated when this is migrating to this nitrogen center. So we will be getting the intermediate N, double bond C, double bond O. So this carbon is already having this methyl group as well as another R group. Then this R group will migrate over this nitrogen. So this will be N plus, and then this will be stabilizing the resulting carbocation. So this is the major product will be this one, option B. Moving to the next question, the major product of the reaction is, so this also I think we have already discussed Lawson rearrangement. So this hydroxylamine will be first rearranged to form the isocyanate. That is, we will be getting N, double bond C, double bond O, and here we have this OH group. So this oxygen lone pair will attack over this carbonyl carbon center, and this will take up the proton from the reaction medium. So we will be getting this compound. So that is option, mm, yeah, C. So the retail mechanism is given here. OH minus will, this will get protonated, and water molecule will be leaving out. Then this will be minus charge will be there, that will come over here. Like this group will migrate over there to form the corresponding isocyanate, and then this hydrolysis, here instead of hydrolysis, this OH minus is attacking over that carbonyl carbon, and we are getting this product. moving to the next question, the major product of the reaction. So here we have this hydroxylamine and treating with this methyl sulfonic acid and this phosphorus pentoxide, which will be the major product. So here the correct answer is this ring expanded product, that is option B, and this reaction is known as Beckmann rearrangement. So what is happening here is that first in the presence of this acid, this is getting protonated and that will leave out as water molecule. So when it is leaving out as water molecule, what is happening, this bond is migrating to this nitrogen center. So we are getting here a resultant ring expanded product, and that migration of that bond to here will result in a mm, carbocation, right? So that carbocation will be generated at this center, and this water molecule, or we can say, yeah, water molecule will be attacking to that carbocation, and then deprotonation we will be getting the corresponding amide. So here a detailed expand, like if we are taking four membered ring in the product, we can get the five membered ring. Here you can see we are starting with a six membered ring and we are ending with this caprolactam, that is seven membered ring. First protonation, then this OH2 will be leaving us water molecule, so this bond will migrate over here to form this carbocation, and to that this water molecule is attacking to form this enolic form, which is tautomerized into this amide, and this reaction is known as Beckmann rearrangement. Next question. This compound upon treatment with the CBr4 PPH in the first step and then butyllithium methyl added in the second step, which will be the major product out of these four options. So this reaction is an example for Corey-Foods homologation. So first what is happening is that by treating with the CBr4 and PPH3, this kind of an intermediate is forming. That is, we can say this kind of an halide is forming Br carbon, and then here this carbon, and this is phosphorus, and this is pH3. So this will be having negative charge and this phosphorus will be having positive charge. So once it is formed, this negative charge will attack over this carbonyl carbon to form this intermediate, and again this oxetane kind of intermediate is formed, which we already see in the case of this viticolination. So once this is formed, then what is happening is that this phosphorus oxide is triphenyl phosphine oxide is leaving to form this alkene, and then once this dibromo-olefin. So here also in the case of aldehyde, the first step will be the homologation, where we will be getting this here this R substituent is there, and here one as proton is there, and here Br we will be getting. Then what is happening after this dibromo-olefin is formed, this butyl lithium will take up this bromine and it will lithiate this position, so it will be Li over here. And then what is happening, this proton will come over here and this Br minus will be leaving. So it will be leaving us LiBr, and we will be getting this lithium acetylide, which upon hydrolysis we will get this terminal alkyne. Not terminal alkyne, we will be getting the alkyne as the product. So here also same thing is happening. Once this R, this proton over here, and here this double bond, and here we will be getting this Br, and here also this Br. Once it is formed, what is happening next is that when we treat with this n-butyl lithium, this will be Li, and then this deprotonation is happening by the second molecule of butyl lithium, and this bromide will leave out with this LiBr, and we will be getting this R, here carbon, and here this triple bond will be there, and Li will be there, and upon hydrolysis we will be getting the corresponding um, terminal alkyne. But here instead of hydrolysis we are using methyl iodide, so we will be getting this Me, yeah, will be attacking over the center, and this I minus will be leaving out, so we will be getting this internal alkyne in this case. So this is an example for Corey-Foods homologation. Moving to the next question, the major product of the reaction. So this vinyl diol we are treating with the sulfur compound and then this phosphorus compound, which will be the major product. So here the correct answer is this trans stilbene, and this example is Corey Winder olefination. So what is happening here is that first these two compounds will form um, yeah, this OH minus is getting converted into xanthate. One of this hydroxyl group is getting converted into the corresponding xanthate. Then this phosphorus will attack over that sulfur, and this bond will shift over here to form this halide kind of intermediate. Then this will leave out to form this carbene. To that again this phosphorus compound is attached to form this intermediate, and then this ring will be opening up, that this bond will shift to here, this bond will shift, and this bond will shift to form this alkene as a major product. So this reaction is known as Corey-Winder olefination. So here also what is happening is that first this O, here also O, then C double bond S will be formed in the first step. Then this phosphorus will attack over this phosphorus will attack over the sulfur, and this bond will shift over here. So it will be O, O, here S, and here P plus, that phosphorus compound will be there, and this will be there. Then what is happening here is that here, as we know, the negative, okay, this is not, this is negative charge, and this sulfur and phosphorus will be bonded. So once this negative charge is here, that yeah, this will leave out, to form the carbene intermediate. So here also we will be getting this oxygen over here, and here this carbene intermediate is there. Once this carbene is there, again phosphorus will attack over that center. Okay. Again this phosphorus will attack over that center, and we will be getting this intermediate. Then upon rearrangement we will be getting this alkene as the major product. Moving to the last question. So here I'm not going to discuss the detailed mechanism. We already know that this is alcohol. We are treating with this nitrobenzoic acid, and the condition itself says this is a Mitsunobu reaction. We will be getting the ester compound, but with the inverted stereochemistry. So the correct answer will be option C. So this is the mechanism of the Mitsunobu reaction. So today, so far, we have seen several named reactions, and which include rearrangement reactions also, and uh, through which is proceeding through various intermediates like isocyanates, ketenes, and we have seen several problems related to those topics. I hope this session was helpful to you. Thank you for joining. See you in the next tutorial session on the upcoming Saturday. Thank you.